Einstein's Theory of Relativity, Simplifying the Complex. Welcome back to our channel. Today, we're diving into one of the most groundbreaking concepts in physics, Einstein's Theory of Relativity. This theory transformed our understanding of space, time, and energy. But let's face it, relativity can sound pretty daunting. So, in this video, we'll break it down into relatable concepts that you can easily grasp and apply to your everyday life. Whether you're a science enthusiast or just curious about how the universe works, stick around as we simplify the complex. To start, let's clarify what we mean by relativity. Einstein's theory is actually divided into two parts: special relativity and general relativity. Special relativity, introduced in 1905, focuses on the physics of objects moving at constant speeds, especially those moving close to the speed of light. It's built on two main principles. The laws of physics are the same for all observers in uniform motion. The speed of light is constant, regardless of the motion of the observer or the light source. General Relativity, published in 1915, expands on these ideas by incorporating gravity and how it affects the fabric of space-time. Understanding these two components is essential because they fundamentally change how we perceive time and space. Now let's break down some key concepts from special relativity. Time dilation. Imagine you have a twin who decides to take a trip in a spaceship traveling close to the speed of light. When they return, they'll be younger than you. This phenomenon is called time dilation. The faster you move through space, the slower you move through time relative to someone who is stationary. It sounds like science fiction, but it's been confirmed through experiments with atomic clocks on fast-moving jets. Length contraction. This concept states that objects moving at high speeds will appear shorter in the direction of motion from the perspective of a stationary observer. Picture a train speeding past you. As it rushes by at near-light speed, it looks squished. However, to someone on that train, everything appears normal. This shows how our perceptions can differ based on our relative motion. Mass-energy equivalence. Perhaps the most famous equation in physics comes from this theory: E equals mc squared. This means that energy, E, and mass, m, are interchangeable. They are different forms of the same thing. A small amount of mass can be converted into a huge amount of energy, like in nuclear reactions. This principle underlies everything from atomic bombs to the energy produced by stars. Relative simultaneity. Events that seem simultaneous to one observer may not be simultaneous to another if they are moving relative to each other. For example, if two lightning strikes hit a moving train and an observer standing still sees them at the same time, someone on the train might see one strike before the other due to their motion. These concepts might seem abstract, but they have real-world implications. Let's explore how these theories apply to our everyday lives. GPS technology. Ever wondered how your GPS knows exactly where you are? It relies on satellites that orbit Earth at high speeds. Because of time dilation, these satellites experience time slightly differently than we do on Earth. If scientists didn't account for this effect, your GPS would quickly become inaccurate. Without relativity, navigating with precision would be impossible. Particle accelerators. In facilities like CERN, particles are accelerated to speeds close to light. Here, physicists observe time dilation and length contraction firsthand. The particles behave differently than expected based solely on classical physics because they're moving so fast. These experiments help us understand fundamental particles and forces in our universe. Black holes and space exploration. General relativity plays a crucial role in understanding black holes and gravitational waves, ripples in space-time caused by massive events like colliding black holes. As we explore deeper into space, understanding these concepts helps us navigate and comprehend our universe better. Everyday technology. Even technologies like lasers rely on principles from relativity. When lasers are used for precise measurements or communications, their operation considers relativistic effects to ensure accuracy over long distances. Now let's shift gears and talk about general relativity, which tells us how gravity affects spacetime. Curvature of spacetime. Imagine placing a heavy ball on a trampoline. It creates a dip in the fabric. This is similar to how massive objects like planets and stars warp spacetime around them. The greater the mass, the greater the curvature. This visualization helps us understand why planets orbit stars. They're following curved paths created by gravity. Gravity as geometry. Instead of thinking about gravity as a force pulling objects together, like Newton did, Einstein proposed that objects follow paths along curved space-time created by mass. This means that planets orbit stars not because they're being pulled by an invisible force, but because they are following the curves created by those stars' mass. Gravitational waves. Einstein predicted that massive accelerating objects would create ripples in space-time known as gravitational waves, similar to ripples on water when you throw a stone in. These waves were first detected in 2015 by LIGO, confirming another aspect of Einstein's theory. The detection of these waves opens new avenues for astrophysics and allows scientists to observe cosmic events that were previously invisible. Black holes. General relativity also predicts black holes, regions where gravity is so strong that nothing can escape them, not even light. Understanding black holes has opened new avenues for research in astrophysics and has led to discoveries about their formation and behavior. Cosmic expansion. General relativity also plays a key role in understanding how our universe is expanding. The theory helps explain phenomena like redshift observed in distant galaxies, an effect caused by space itself stretching as galaxies move away from us. Einstein was famous for using thought experiments to illustrate his theories. Consider his famous train thought experiment involving lightning strikes mentioned earlier. It helps us visualize how observers moving at different speeds perceive events differently. Another thought experiment involves imagining what happens if you could travel alongside a beam of light. What would you see? This led Einstein to conclude that light behaves differently than any other object we experience daily. One more thought experiment involves imagining being inside an elevator accelerating upwards. You would feel heavier due to acceleration mimicking gravity. This illustrates how acceleration can be indistinguishable from gravitational effects, a key insight leading to general relativity. These thought experiments help us grasp complex ideas without needing advanced mathematics. In conclusion, Einstein's theory of relativity fundamentally changed our understanding of time, space, and gravity. By simplifying these complex ideas into relatable concepts like time dilation with twins or GPS technology, we can appreciate their relevance in our everyday lives. Thank you for joining us on this journey through relativity. If you found this video enlightening or would like to discuss Einstein's theories or their applications, please leave a comment below. Don't forget to like this video and subscribe for more engaging content about science and philosophy. Let's keep exploring our universe together.